Hi, good morning, everyone, and welcome again to those of you who were with me last Thursday, and welcome to any newcomers who weren't attending the session last Thursday. My name is Cliff Curtis, and I'll be your presenter for today's session. This is the second in two sessions on Pearson Edexcel International A-Level Chemistry. Welcome to Pearson to give you an introduction of this particular qualification and let you know what it's all about. And the aims and objectives of today's session is to understand the question types for this particular qualification, to understand the assessment objectives for this particular qualification, to practice using the mark schemes, using some exemplar student material. They'll give you an opportunity to have a look at some answers that were given by students in past papers, an opportunity to see how they were marked and see what students did well and did not so well. And then finally, to learn about the support provided by Pearson around the assessment and the exemplars. So today's agenda will be, first of all, looking at the question types on the International A-Level Chemistry papers. And then, as I said, looking at the assessment objectives and what they're all about and the reasons why we have them and why they're so important in the production of the exam papers. And then we'll look at some of the AO2 questions. If AO2 doesn't mean anything to you at the moment, hopefully that will become clear as I progress through the presentation. And then we'll look at AO3 questions and then look at the supports available. I just see that some chat material has come up here. Okay. You can look at the bottom of your screen. I forgot to mention a couple of housekeeping points. There is a resources tab down at the bottom, and you can access and download all the resources material for to support this particular session today. You won't need to look at the resource material during the course of the presentation because I've put everything onto the slide screens. The other thing that you need to have up is the chat box. So if you click on the chat box, that's your method of communicating with me if you want to ask any questions during the course of the presentation, okay? And I will try and keep an eye on that chat box. Okay, so off we go. Let's have a look at the various different question types. The following question types will be set in units 1, 2, 4, and 5. For those of you who were with me last Thursday, you will remember that these are essentially what you might call the theory papers in the 6 particular units on which papers are set. Units 1 and 2, of course, are for the International Advanced Supplementary qualification, and units 4 and 5 are for the International A-Level qualification. There will be multiple choice questions with 4 alternative answers labelled A, B, C, and D. There will be 20 of these, and they will be at the beginning of the paper. And the way in which you go about them, marking them, we'll look at in a moment. Short response with a mark range of 1 to 5. Extended writing worth 6 marks, but they will be only in units 2, 4, and 5. There will be none of the extended writing questions in units 1. And of course, because chemistry is a numerical subject, there will be calculations. Units 3 and 6 will focus on solely on practical skills. There's a typical multiple choice question. The method of answering the multiple choice question is simply to put a cross in the box to the left of the letter. If a student wishes to change their mind, they put a line through the cross and then put a cross in another box which they wish to be considered as their answer. If they make a complete and utter hash of this and finish up with lines through all 4 boxes, then advise them simply to write the letter, and that will be picked up at a later stage and will be marked manually rather than by the computer. There's a typical short response question. This one is only worth 2 marks. You will see that there are a lot of lines left, 6 marks left. That is much more than is needed to be able to answer this particular question. Students should not feel that they have to fill up all the space available, and the time that they spend on a particular question should be reflected by the marks available. In general, they should be spending about 1 minute per mark, so no more than 2 minutes to answer that particular question. The reason why we leave more space is because some students don't give sufficient thought prior to starting their answer to a question, and then suddenly realize that they are answering the question along the wrong lines and have to cross out their work. And in those circumstances, there's usually enough space available for them to do another one. Okay, there's a typical extended writing question. Worth 6 marks. In this particular question, marks are awarded for what we call indicative content and how the answer is structured. The next slide will show how this is done. The number of indicative marking points is usually, there are usually 6 of them. If they get all 6 of the indicative marking points, they score 4 marks. If they get 5 or 4 of them, they score 3 marks. 3 or 2, 2 marks. If they only get 1 of them, they will get 1 mark. And obviously, if they don't get any of them, they're not going to score. In this particular question that was set, there are the 6 indicative points. So they would have to have got all of those 6 marks, those 6 indicative points, in order to be able to score the first 4 of the points. So how do they get the next 2? Well, the next 2 relate to the way in which they structure their answer and the lines of reasoning, so linking the points together. So if their answer shows a coherent logical structure with linkages and fully sustained lines of reasoning, they will get 2 marks. If the answer is only partially structured with some linkages and lines of reasoning, they'll get 1 mark. And obviously, if there's no structure to it, they will score 0. And you can see in the right-hand column there, in general, it would be expected that 5 or 6 indicative points would get 2 reasoning marks, 3 or 4 indicative points would get 1 mark, and 0, 1 or 2 indicative points would score 0. Notice that if there is any incorrect chemistry, the examiners are told that they must deduct marks from the reasoning. If there's no reasoning awarded, they don't deduct marks for any incorrect chemistry. Okay, so that's a very good point for you to make to your students, that they shouldn't just put information down at random, because they may be penalized if some of the information they put down is in fact incorrect chemistry here. So they should stick to the point about answering the question. Okay, there's a couple of calculations. One of them worth actually 6 marks. They're first of all asked to write an equation for the decomposition of sodium azide, and then to do a calculation based on that equation. Obviously, if they get the equation wrong, then the calculation in part B will be marked according to the molar ratio that they have got within their equation. So they wouldn't be penalized for having an incorrect equation in the calculation. Whatever mole ratio they happen to get in the equation would be carried on into calculation B. And it's quite a tricky calculation, that one, and hence the reason why there are 6 marks allocated to it. It makes use of the equation PV equals nRT, in which they have to rearrange to make n the subject of the equation and then substitute in and solve. I think I used this slide on last Thursday, but never mind, we'll use it again. Don't put any answers into the chat box, please, and don't put any marks onto the screen, but just simply have a think about that particular question What are the essential points to include when answering the following two questions? To complete that dot and cross diagram and then explain the shape of the molecule. So have a think, keep them in your head, jot them down on a piece of paper if you like. Okay. I'll give you a minute or so just to have a think about that particular one. Apologies for those that were with me last Thursday for taking you through the exercise for a second time, but there may be some here today that weren't with me last Thursday and may like to have a think about that particular exercise. Okay, my suggestion here is that for the dot and cross diagram, they should include the bonding pairs and then the non-bonding pairs on both the oxygens and the chlorines to get the second mark. And for the shape, they should write down the exact shape of the molecule, first of all, and then mention that the regions of bonding electrons repel one another and they adopt positions of minimum repulsion. That is the best and simplest way to answer any question dealing with shape of molecule. Write down the shape, just simply say the regions of bonding electrons repel one another. Don't talk about bonding pairs or anything like that, because sometimes the region of bonding electrons might well be 4 electrons. Indeed, in one of the dot and cross diagrams you can draw for the molecule on the in this question, you can in fact have 4 electrons in being shared between 2 of the atoms. So it's best simply just to say regions of bonding electrons repel one another to adopt positions of minimum repulsion. I would very strongly suggest you show this particular slide to your students as an exemplar way of answering this particular question. And tell them, keep to that answer. It's so simple, so straightforward. Okay. You may be wondering, why have I asked you to carry out this type of exercise? It's because I always encourage my students when they were answering their questions, both at GCSE and A-level, think about what are the essential points to put into the answer before you start writing your answer, so that you don't start off on the wrong track, have to cross out and then start rewriting your answer. Give some thought to your answer before you start writing. So I would suggest it might be a good idea to share this particular activity with your students. Right, here's activity 2 for you. Again, don't write your answer into the chat box. Okay. Why is iodine very soluble in cyclohexane, but is only slightly soluble in water? Again, have a think about what the essential points are to write, and then think about how you construct your answer. Again, please don't put any answers into the chat box. There are over 20 of you in the room at the moment. We haven't got the opportunity to read everyone's answer, so effectively you will be wasting your time. So just jot your answers down on a piece of paper or keep them in your head. And then I will share with you what I would have written down should I have been answering this question in an exam. So the first thing I would have put down is that cyclohexene and iodine form London forces between their molecules. So iodine is soluble in cyclohexane. Both molecules are non-polar, so the only forces between them are London forces. You could, of course, have said instead of saying using the word London forces, you can describe the forces in terms of temporary dipoles, induced dipole forces, or instantaneous dipole, induced dipole forces. But I don't see why students want to write that when it's much quicker to write down London forces. Try and avoid the term van der Waals forces. I know they allow it in the mark schemes, but van der Waals forces are not just London forces. They are, of course, all intermolecular forces of attraction, including permanent dipole forces. That's permanent dipole, and permanent dipole-induced dipole forces are all van der Waals forces. And indeed, if you're an organic chemist, you will probably include hydrogen bonding in van der Waals forces as well. I would suggest that you never mention the term van der Waals forces in your teaching. That would be my very strong suggestion. Don't even mention it. Don't go there. Just keep to the names of the forces that are listed in the specification. And secondly, the reason why iodine doesn't dissolve in water is, of course, because the hydrogen bonds between the water molecules are stronger than the London forces between iodine and water molecules. So iodine is much less soluble in the aqueous layer. It will dissolve very, very slightly. If you want to increase its solubility, you will, of course, add potassium iodide, because the iodide ions will react with the iodine molecules to form the triiodide ion I3-, and it becomes much more soluble. But it's not very soluble in just pure water. Okay, so I did mention that after we look at a little bit about the question types, that we will, in fact, look at the assessment objectives. Just let me have a look, see what's coming to the chat room. Do they have to use full word permanent dipole, permanent dipole? I would advise them to do so, because the specification says permanent dipole, permanent dipole. It would have been much better if they'd have just said dipole-dipole attractions or permanent dipole-dipole attractions, because, of course, there are two types of permanent dipole attractions. There are permanent dipole attractions and permanent dipole-induced dipole attractions. The first are called Keeson forces, and the second ones are called Debye forces, after the scientists who first put forward the suggestions of those two. So my recommendation is tell them to put down permanent dipole, and not just permanent dipole. I would hope that permanent dipole would be marked correct, but I'm giving you my advice there. Okay, so why do we have these particular assessment objectives? I'll go through what they are in a moment, but let me give you some reasons why they are actually there. It is to help make the exams fairer year on year, and I hope that will become clear in the slides that follow. It provides a structure for writing questions, papers. So I will, again, hope that will become clear in just a moment. To make sure the exam's about skills and not just about knowledge. Again, I'm hoping that will become clear in a moment. And it can provide the students with some reassurance about the types of questions that they will, in fact, be asked. So how are all these objectives met? Well, there are the four assessment objectives. AO1, AO2 is split into two, AO2A and AO2B, and then there's AO3. AO1 is all about demonstrating knowledge and basic understanding in science. AO2A is about the application of knowledge and understanding of science in familiar and unfamiliar contexts. AO2B is about analysis, evaluation of scientific information to make judgments and to reach conclusions. And AO3 is about experimental skills in science, including analysis, evaluation, data and methods. AO3 will only appear in units 3 and 6, and AO1, AO2 and AO2A and AO2B will only appear in units 1, 2, 4 and 5. The types of questions that will be set, well, for AO1, you will get questions requiring students to recall and use the information that you have in fact taught them. Questions in AO2A will require students to apply what you've taught them. or to use skills, then that could be to familiar or unfamiliar situations. And AO2B, the questions will require students to analyse and make judgments, which is obviously a slightly higher level skill in Bloom's taxonomy. And AO3 will be solely on questions on practical work and associated practical skills, such as planning, drawing graphs, drawing apparatus, analysing data, evaluating methods, spotting things like procedural errors, explaining how you could overcome those procedural errors, knowing about any risks that are involved in experiments and how to minimize the effect of those risks when you perform in experiments, etc. So all about the associated practical skills, which you can, of course, your students can obtain by doing the core practicals that are listed in the specification. The way in which, of course, we make the exams fairer from one year to the next is that there are a certain percentage number of marks that have to be made available on any exam paper. They have to be set on any exam paper for AO1, AO2, and AO3. And because that percentage is fixed, then one paper from one year to the next will, of course, contain roughly the same percentage of marks, AO1, AO2, and AO3. So that way, the exam's made fairer from one year to the next. That way, the level of demand and degree of difficulty is kept very much the same, and it gives it enables you to know what the makeup of the paper is, so it gives you some confidence and the students some confidence about knowing what sort of makeup the paper will have from one year to the next. So let's have a look at some typical AO1 questions. There is one, a multiple choice question. The specification states that students need to know what is meant by covalent bonding, and because it is a no statement in the specification, that of course is straightforward recall. So that they need to know that it is the electrostatic attraction between two nuclei and a shared pair of electrons. Draw an electron density map for a molecule of oxygen. That is a specification point. They need to know the density map for a molecule of oxygen, and they do need to know the shape of the water molecule, and they need to know its bond angle. So they are AO1 questions. AO2A, there's a typical question. What is the electronic structure of the scandium 3+ ion? Well, that is not a no statement in the specification, but of course they do need to know the electronic configuration of the scandium atom, and therefore they need to know which 3 electrons are removed when you form the scandium 3+ ion. Therefore they have to apply their knowledge of, one, the electronic configuration of the scandium ion, and secondly, the knowledge of which electrons are removed first when the transition metal ions, well, this is a transition metal, when the D block metal ion atom forms an ion. So that is AO2A. And there's an AO2A question. It's a calculation. The majority of calculations will be AO2A. Some will fall into the category of AO2B when they have to utilize data that's supplied in a slightly different format, but most calculations will be AO2A. A typical AO2B question is that one. The reason why this is not AO2A is because there is no scale given on the vertical axis, and therefore they have to make judgments based on the height of those bars in the bar chart there. So that is an AO2B. They have to analyze and produce an estimate. And there's a typical AO3 question. Don't bother reading through the whole of the question. You will have the slide pack in the resource material, which you can download and read through later. But you can see, if you have a quick read through it, that everything there is all associated with practical work and practical skills. So I'll just have a look at the chat box. Since they're given a periodic table, they don't need to know the atomic number of a certain element because they can check it out. You are correct. They are given the periodic table, so they do not need to know the atomic number of a particular element. Okay, don't apologize for being a newcomer. That's what this presentation is all about. It is a welcome to Pearson presentation, so it's specifically designed for the newcomers. You're welcome. Okay, so let's move on to activity number 3, and this gives you an opportunity, having learnt what the various assessment objectives are, to assign some assessment objectives to specific questions. And there's the first one. Again, please don't put your answers into the chat box because there are too many of you here. We haven't got the opportunity to read all of the information. So if you want to share this with your students later, then just jot down the answers so that you know what the correct answer is and you can advise your students accordingly. I'll explain why I think it's useful for students to undergo this sort of exercise in a moment. So the question you've got to ask yourself is this recall of knowledge direct from the specification? Should they know about the structure and properties of sodium chloride? The answer, of course, is yes. The one that is not true is C. It is a giant ionic structure, not a molecular structure, but it is recalled, so that is in fact AO1. You'll be amazed at how many students, even at A level, think that ionic compounds have molecular structures. I have no idea where this idea comes from. I can understand it to a certain extent with things like silicon dioxide, because it's often described in many student books and on websites as being macromolecular, which is not really a correct terminology for silicon dioxide or diamond or other giant covalent structures. They should be described as giant covalent structures. And I know the mark schemes do allow the answer macromolecular here. It's not a correct term, and I would suggest that you avoid using it and just simply refer to these types of structures as being giant covalent structures. Macromolecules are polymers as defined by the chemistry rubber book. Macromolecule is not the correct term for it. Okay, there's a second one. What is the assessment objective there? But if that question had incorporated a temperature rise and they were asked to calculate the enthalpy change of neutralization there, or they were asked to calculate the energy release, that would be a straightforward substitution into the equation. MC delta T, but this time they have to calculate a rearrangement here and get delta T to be the subject of the equation. And as a result of that, that particular example was classified as AO2B. As told you earlier, that the very majority of the calculations will be AO2A, but this particular one is AO2B because they have to make some form of judgment here. Okay, there's the next one. Which of these sulfates is least soluble in water? So you have to ask yourself the question, are students expected to know the trend in solubility of sulfates in group 2? And are they expected to know that group 1 metal sulfates are soluble? And the answer to both of those questions is yes. So that is in fact an AO1 targeted question. The next one, oops, I put up the answer. This time it is a straightforward calculation, a straightforward substitution into an equation to calculate the enthalpy change of formation of methane from the data given. and therefore that is AO2A, not AO2B. I hope you can see the difference between the two different calculations that I gave you. Okay, the next one, this question is about fuels in polymers. Used ground coffee grounds can be suggested as carbon neutral fuel to place some fossil fuels. Explain why coffee grounds might be considered to be carbon neutral. So students are expected to know what is meant by a carbon neutral fuel, but of course the coffee grounds are not specifically mentioned in the specification, and therefore students have to apply their knowledge to work out why coffee grounds could be considered to be carbon neutral. So that part of the question is AO2A. And then explain how the use of fossil fuels causes climate change. Climate change, of course, is a recall statement from the specification. They need to know about climate change and how fossil fuels cause it, and therefore that is AO1. Okay, the next one, alkenes such as ethene can be used to make polymers. Write a balanced equation. Balanced equations, chemical equations will almost certainly be AO2A. Bananas produce ethene as they ripen, suggest one advantage and one disadvantage of using ripening bananas as a source of ethene for polymer production. Well, this, of course, requires students to make a judgment here, to come up with an answer based on the data that they've been given, and therefore that will be classified as AO2B. A sample of ammonium carbonate was dissolved in distilled water and the solution tested. Complete the table to give the expected observations. Pretty obviously that is experimental work, and therefore that would appear on a Unit 3 paper, although it could appear on a Unit 6 paper as well, and that is AO3. Okay, another aspect of the exam papers is the use, of command words. All of the questions in the exam papers are designed to use specific command words to guide students. So technically speaking, they're not questions. The only questions that can be set are in multiple choice. Any other questions, short response, calculations, extended response, all have to make use of command words. The list of command words is listed as an appendix in the specification, which you can download from the Pearson website in the section about international advanced level chemistry. One of the things I always used to do with my students was to get them to download that appendix for themselves and to print it off and put it in the front of their folders. And every time they came across a question in inverted commas, they had a look at the command word, identified what the command word is, and then look at their list and see what the demand of that command word is, so they knew exactly what they had to do. Okay, the command words represent a range of skills. So, for example, simple recall would be command words like give, name, or state. Using knowledge would be describe. Given reasons would be explain. Interesting that explain, you've got to be very careful about the explain, because it's now a requirement that exam paper writers cannot use two command words in the same sentence, and therefore can no longer write down state and explain. So if a question said, explain how the rate of the reaction between magnesium and hydrochloric acid changes as the concentration of the hydrochloric acid increases, then of course they have to first of all state how it changes, i.e. the rate of the reaction will increase, and then offer their explanation. So students need to recognize that explain could effectively mean state and explain, and not just explain. So do make your students aware of that. Provide more detailed analysis, evaluate, justify. That will be very common in evaluate, will be very common in AO3. Justify will be very common in AO in the theory papers. So, for example, a one sentence could be state what is blah, 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 and a second sentence could be justify your answer. Show particular skills like calculate or plot. Calculate, of course, could be in any of the 6 exam papers. Plot, of course, is going to crop up in AO3, so could be in units 3 and 6 when they're asked to plot graphs. Is there a link between command words and AOs? Well, I've given a little bit of an insight into that. I think there is some degree of link, but there's also quite considerable overlap. So there's some examples of the command words that may well crop up into AO1: add, label, complete a table, describe, straightforward, known ideas, draw. That could be draw the shape of a molecule, or it could be draw, sketch a graph, or it could be draw a piece of apparatus. Explain a simple idea or reason. Notice that it's straightforward explanations in AO1. Give, state, name, or state. Write a very familiar equation. Could be AO1, could well be AO1. If it's a very straightforward equation, then that would not crop up into AO2A. AO2A, calculate, comment on, deduce. Determine also follows in there. Deduce and determine are not the same, because determine requires the students to give some mathematical support to their determination. Deduce doesn't require mathematical content. Evaluate, explain for more complex ideas. Suggest, write for an unfamiliar or more complicated equation. AO2B, comment on, deduce, evaluate, explain, and suggest. AO3, virtually any command word can be used in AO3. So I would suggest you make yourself very familiar with all those command words, and make your students very familiar with them and the requirements for each command word. Okay, so let's now have a look at some AO2 questions. You may be wondering why I'm not going to look at AO1. Well, to be quite honest, AO1 is all about knowledge and basic understanding, and it's not one that you can influence much. I doubt very much if you've got an awful lot of time to constantly test them on recall. You may be able to set a few small tests on recall, but I don't think you can constantly test them on recall. You've got to really rely on them to go away and learn what you teach them. They either do that or they don't. If they don't bother to learn the no statements in the specification, there's very little that you can do. And in fact, they're not going to do themselves much justice, because, of course, that knowledge is required because they need in AO2 questions to apply their knowledge. And if they haven't got the knowledge, well, of course, they are really struggling. But I think students should be able to still recognize AO1 questions and not spend time going beyond AO1. As an examiner, I first started examining for Edexcel in 1988. Started marking GCSE papers, moving on to A-level, becoming a team leader at A-level. And then I was principal examiner for the Edexcel International GCSE Chemistry from 2010 right the way through to the end of 2017. So I have seen literally thousands of examination scripts, and the number of students that give enormously detailed answers to questions that require very simple and very straightforward answers, i.e. they fall into the category of AO1, well, if I had a pound coin for every single time I've seen that, then I'd be a very, very rich man by now. Students should not be spending a long period of time answering AO1 questions. They should be confining themselves to very, very simple answers. So they should be able to recognize AO1 questions, which is why I think it's useful for you to carry out an exercise where you give them some AO1, AO2 questions and ask them to try and classify which ones are AO1 and AO2. And you can get AO1 and AO2 questions from Exam Wizard. Right, so what I'm now going to do is get you to jot down on a piece of paper the marks that you give for these questions. We'll go through them one at a time. We probably won't have time for you to be able to spend time marking every single one of these, but I'll at least get you to mark the first example of them. Here's the first question. In some air bags, solid sodium azide decomposes to form nitrogen gas and sodium. Write an equation. The correct equation we'd expect to see is the one shown there. 2NaN3 gives 2Na plus 3N2. Accept multiples. So accept those two. If they double it up, that's allowed as well. Ignore state symbols, even if incorrect. State symbols have not been asked for. If the state symbols asked for, they must be given for the second mark and they must be correct. But if they're not asked for, we ignore them. There will be a number of candidates who write down Na2. They seem to think that metals are bimolecular compounds, and obviously that must be marked incorrect. So do not award that. So go through those and make a decision for yourself as to whether or not they're correct or incorrect. And then I'll share with you what I consider to be the answers. Shouldn't take you too long. The first one is obviously wrong because it has got the wrong formula. It's got sodium oxide in it, not sodium, and N3, which is incorrect. The second one is correct. It's the model answer. The third one is correct because it has been divided by half, and that's perfectly acceptable. And the last one is wrong because they've got Na2. So a good one, I think, to share with your students to show how students do make mistakes, okay, and get them to mark it. Okay, the next question, explain the trend in thermal stability of group 2 carbonates. Now, this, of course, falls into the category of a state and explain. So they need to state what the trend actually is. So the first mark is for stating that group 2 carbonates increase in stability as you go down the group. And then the explanation goes into the falls into the realm of the size of the metal ion or cation increases, or the charge density of the ion decreases. Notice that the word metal doesn't need to be present. Ion does. Charge density decreases. On this occasion, they don't need to state it's iron because of iron is in brackets. Okay, so the metal is less polarizing, or the anion is less distorted. Preferably, we'd like them to say the electron cloud of the anion is less distorted, but electron cloud is not essential because it's in brackets. So weakens the bonds in the carbonate ion. Less or more energy is needed to break the bonds in the carbonate ions. We would like them to say that they're covalent bonds, but covalent is in brackets. So anything that's in brackets is what we would like them to put in, but they don't have to include that information. It's useful when you go through mark schemes with your students to point out that that isn't absolutely necessary for this particular question, but do point out to them in a future exam, they may be necessary. What's in brackets for this particular mark scheme may be necessary in a future mark scheme. Don't assume that what's in brackets will be in brackets in a mark scheme in a paper that's going to be in the future. Okay, so here we go. There's the first question, and I'll let you have a think about how many marks and which marking points are present in that particular answer. And then the others, I will go through them with you one by one, because of course we haven't got enough time to give you the time to mark all of them. But I'll give you a chance to mark that particular one. I've left the mark scheme up on the screen for you to see. So which marking points are present in that answer? Well, the only marking point that I can find that's worthy of credit is the third bullet point, which I'm going to call M3, for the distortion of the electron cloud decreases down the group. That's equivalent to anion less distorted. In the first sentence, the student says the carbonates decreases, so that is wrong, so they can't have M1. M2 would have been awarded, it would have been given for the size of cation increases, but unfortunately the candidate later contradicts this statement by saying that the size of the cation remains the same. So they've got some correct and some incorrect contradictory chemistry, so that mark cannot be awarded. And there's nothing about weakening the bonds in the anion, the carbonate ion, so there's no M4, that can't be awarded. Okay, so I hope you agree with me on that particular marking. That's a good one to show your students for contradictory information, losing a mark for good chemistry. So I would advise you to share that particular student answer with your students. Okay, there's the next one. I think there are a couple of marks that you can award here. If you go right down to the very end of the answer, there's M1, and just above it, there's M3 for the distortion of the carbonate ion decreases, and M1 for thermostability of group 2 carbonates increases. I can't find any reference to the iron, mention of the iron when describing the increase in size. And it does say over here, size of metal iron with iron in bold type. So since there's no mention of iron when describing the increase in size, I'm not prepared to award M2 there. They have to mention the iron. Okay, they could have got away with charge density decreases, but they say charge density remains the same, so they can't have that particular mark. Again, there's no mention of the weaken the bond, so M4 cannot be awarded, the fourth marking point. Okay. Okay, I hope you're happy with my solution to that particular one. So this candidate gets 2 marks. Okay, right, there's one more that we can look at. This candidate starts off by saying, going down group 2, the stability of the carbonates increases, which is the first marking point. It then goes on to say this is because going down the group, the ionic radius of the cations increases, so they can have the second marking point. Then they go on to say in the last sentence, this causes the anion to be less distorted, so they can have the third marking point. And this one, finally, someone says the CO bond is less weakened and the decomposition ability decreased. So there we are. They can score 4 points. So that's a good answer and an excellent one to show your students. Okay, so I hope that's been useful for you in showing you how a short response question with 4 marks is answered and giving you some indication of what students do well and don't do quite so well. And as I said, you may want to share that with your students. Okay, the next question, alcohol Y has the structure shown. Y reacts with concentrated phosphoric acid to form 4 isomers with the molecular formula C10H18. Draw the skeletal formula of the 4 isomers formed in this reaction. So there are the 4 isomers formed, and the additional guidance says allow any unambiguous type of structure, and that will include bond angles that are not as we would like them to be. So if they're given correct bond angles, then that is okay, as long as the structure's unambiguous. Obviously, they couldn't give a 180-degree bond angle for the right-hand side of the structure, as long as, but the bond angle doesn't have to be 120 degrees. It can be something slightly different. It could be 90 degrees, for example. That's not a problem. Okay, so let's have a look at some student answers. There's the first one. I've left the 4 correct responses up for you. Decide for yourselves on that one which of those are correct. And hopefully that wasn't a too difficult one for you. You should be able to spot that that one's correct, that one's correct, that one's correct, and that one is incorrect. So this student scores 3 marks. There's the second one. Well, that one is correct. That one is correct. Ignore the incorrect bond angles there. As long as the structure is unambiguous, it's fine. That one's correct. And that one's correct. So this candidate scores 4 marks. I just leave you to convince yourself that all of those are in fact correct. Okay, there's the third student. Not the sort of bond angles we would like to see, but which of those are correct and are any incorrect? Not the best drawings in the world, but they are all acceptable. They're all correct. So that candidate scores 4 marks. Excellent examples, I think, again, to show to your students and emphasize to them that it would have been far better if they'd have given the structures shown in the mark scheme rather than the ones that are shown here, that they can get away with it, but it's better if they write down their structures in the way in which we expect to see them. Okay, so let's have a look at some AO2B type questions. The first one is burning polychloroethene incinerator results in the formation of hydrogen chloride. Suggest how the hydrogen chloride could be removed from the waste gases produced in the incinerator. The first marking point is for the use of a basic or alkaline substance, or to form a precipitate or a salt or a solid is an alternative answer. Note it's underlined, so they're the three things that are acceptable. In the additional guidance, it says allow named examples of a basic or alkaline chemical. So ammonia, sodium hydroxide, calcium carbonate. Scrubbers alone is not sufficient. Or injection of a powdered activated charcoal, accept adsorption in granular activated carbon. It's got to be AD, and not AB, or coke beds, or pass through water or dissolve the hydrogen chloride in water. Notice that dissolve is underlined, so that word has to be there. Allow dissolve in steam, ignore fractional distillation of gases, and do not award general descriptions of recycling. Okay, so there's the first answer. And unfortunately, 1 mark for ammonia has cropped up immediately because I flicked it too quickly. But I think you'd have got that answer pretty quickly. So ammonia is acceptable. The second one, the gases can be passed into a fractionating column, and the hydrogen chloride can be condensed off, of course. That is no marks because the mark scheme says ignore fractional distillation. Okay, sorry, I flipped through that one a little bit quickly, so I'll give you the opportunity to answer the second one. So work out the answers to those for yourself. With additional guidance says scrubbers alone is insufficient, so no marks. Second one, put the waste gases through a base like sodium hydroxide. The HCl reacts with sodium hydroxide. The additional guidance says a named alkali, but they've said base anyway. So 1 mark for pass the gas through a base. Okay, the next question. These questions, by the way, were all taken from June 2019 exam series. Every question that appears on this presentation, June 2019 exam series. Right, we've got propanoic acid, colourless liquid, preservative and animal feed. It can be formed by oxidizing propan-1-ol. Okay. Propan-1-ol is heated with a concentrated solution of acidified potassium dichromate 6. A student suggested using universal indicator to check for the presence of propanoic acid formed in the reaction mixture. Give a reason why this result is not likely to be conclusive. And the reason, of course, is that the colour of the potassium dichromate, or the chromium-3, will mask the colour of the indicator, or the reaction mixture will contain hydrogen ions or acid that's present from the original oxidizing agent. The additional guidance says ignore references to not a sharp colour change, and you can allow any named mineral acid. Okay, so there's student 1, student 2. Their answers. How many marks are you going to give for student 1? I'm going to give a mark for student 1, and I'm going to give a mark for student 2. Additional guidance says allow any named mineral acid, so 1 mark. There's no mark there for range of indicators. That doesn't answer the question as set, so no marks. Those 2 answers. Well, the answer to 3 is a very good one to show your students, because they would have got the mark for hydrochloric acid, but they lose it for stating that propan-1-ol is acidic enough to affect UI. So that's an excellent one to show your students about how writing extra information that happens to be incorrect chemistry negates the mark that the student actually got for putting down some good chemistry. So, good one to show your students. What about the next one? The reaction mixture turns green when oxidized, so the color indicator was shown. Well, I think that covers the first answer in the script. So I would give 1 mark for green color not allowing the color to show. Okay. Hope you all agreed on that one. Okay, right. Well, that's just a brief introduction, a little bit of introduction into marking. Okay, if you happen to be in either Macau on the 14th or 15th of this month, so that's next week, isn't it? Yeah. I will be in Macau, and I'm giving face-to-face demonstrations on understanding assessment and improving delivery, in which there's an opportunity for the delegates to do a lot more marking. So if you do live in Macau or in Macau on those 2 days, then go onto the Pearson website and sign up for that particular presentations, either one. The first one's on international GCSE, the second one's on international A-level. The following week, I will then be in Hong Kong on the 18th and the 19th of March, doing the same 2 presentations. And then the next week, I will be in China, in Chongqing, doing exactly the same 2 presentations on understanding, assessment, and improvement delivery on international GCSE and international A-level chemistry. If you happen to be in China and can get down to Chongqing, then I suggest you sign up for those 2 as well. And if you do, I'll be looking forward to meeting you there. Okay, so here's some questions for you to think about after we finish this particular presentation. Teaching approaches. Is it better to prevent facts or to teach principles in why? Well, AO2 is all about understanding, applying your knowledge and understanding. So I think it's pretty obvious that the straightforward teaching of facts will not help them with AO2, except for the fact, of course, they do need to know the facts. So facts on their own, not good enough. You need to teach principles. Okay. Is it better to ask closed or open questions? Well, closed questions are those requiring just a factual answer, a single answer. Whereas, of course, open questions require students to think about the question and give an explanation or justification or evaluate something. So obviously, that's going to be a better preparation for AO2. Is it better to set formative or summative assessments? Summative assessments are where you are just simply interested in the score that the student has got, and you put the students into rank order so that you can see which students were the best in that particular topic and which were not so good. The formative assessments are where you actively give students feedback on what they've done well and what they've done not so well. And I think it's pretty obvious which is the better type of assessment to give to your students to prepare them for AO2. And what else could you do to prepare your students to answer an AO2 questions in the exam? Well, one solution, of course, is to give them lots of practice in answering AO2 questions. And where can you get these? From Exam Wizard. Now, I talked a bit about Exam Wizard last Thursday. You need to sign up for Exam Wizard. Well, you need to get a username and a password, which you can get from your exams officer or from your principal or head teacher. And then you simply then type into your search engine Pearson Edexcel exam wizard. It will take you to the login page. You log in, and there is a detailed drop down teaching you how to use Exam Wizard. And one of the ways you can use Exam Wizard is you can pick out from past papers AO2 questions and AO1 questions and AO3 questions. Okay, question styles. Something for you to think about when you go away. Think about one of the topics you teach, which often has AO2 questions in exam. What sorts of questions do you ask in class when teaching this topic? And how do these questions help your students to prepare for AO2? So I'm just sort of encouraging you to think in advance about the type of questions that you do actually ask during your lessons. And if you are required or you do yourselves write lesson plans, I would very strongly recommend that you actually jot down those questions into your lesson plans. So do give some thought prior to teaching a particular topic, what questions are worth asking in order to get your students thinking about applying their knowledge and understanding. Homework activities as well. Think about homework. Why do you set homework? Is that simply because you're told you have to? Or do you set it for a reason? And if so, what sort of questions or problems do you set? And what do you expect the students to gain from what you set? Will they gain? What will they gain? Help them to answer AO2 questions. So again, I'm encouraging you to give some very creative thought as to the homework questions that you actually set, and not, as I did when I first started teaching, just simply go through setting homework because I had to set it. I didn't give an awful lot of thought to what I set for homework. As I became a more and more experienced teacher, I gave a lot more thought to it. And by the time I got to the end of my 38 years of teaching, I hopefully was setting homework that was pretty valuable to them. At least I would hope so. Okay, so let's spend the time now having a look at some AO3 type questions. And what is AO3? Well, let's have a recall of that. It assesses the practical skills and understanding gained by students as they undertake practical work. The questions may require recall of the practical techniques and understanding or application to these new situations. So it may recall practical techniques of the core practicals. So the students may well be asked to recall the procedures of the core practicals, which is why they need to be aware of every single one of the core practicals listed on the specification. In an ideal world, they should have hands-on experience of every single one of those core practicals. Where that is not feasible, the next best thing is for them to see a demonstration of that core practical. And if that is completely impossible, try and find a suitable video to demonstrate this. Lots of videos are present on the Royal Society of Chemistry website. In fact, I helped out a colleague of mine in Cyprus just recently, just before Christmas, who was taking maternity leave. I took all her A-level lessons for 6 weeks, and I made extensive use of some of the video clips on the Royal Society of Chemistry website in the teaching of organic chemistry. And I found them extremely useful. So do go onto the Royal Society of Chemistry website and go into the teacher resources and look at the video clips that are available. But do be aware, of course, that they will be tested not only on those core practicals, but the application of the skills and understanding and knowledge they've gained from those core practicals and apply that to unfamiliar experiments. Lastly, it may involve the use of experimental data and the evaluation of experimental methods or results. There's a recall of a practical technique. Describe how the student should use the apparatus to determine the melting temperature range of a sample of their crystallized methyl 3-nitrobenzene. So recall of a practical technique. There's an example of analysis of results. This is a question that we'll be looking at in a moment, so I'm not going to dwell on it too much. Well, we're going to do something very similar, but not exactly the same. They're told that they've got a white precipitate formed in adding dilute sulfuric acid and asked what two possible cations could be present. Okay, and then in the second one, a sample of A was heated in a test tube, glowing splint was put in, the splint relight, and brown gas was evolved. What anion is present? Okay, so that's analysis of results. And then part two, two gases evolved when A was heated, brown gas C, and D, which relights a glowing splint, identify the gases by giving their name or formula. Okay, a little word of warning down there, by the way. If the students decide to give the name and the formula, and one of them is correct, they will get penalised. If they do give the name and the formula, which they don't have to do, but if they do decide to give both must be correct. Otherwise, they will lose a mark. So that's another point that's well worth making to your students. There's another analysis of result question. Again, don't bother reading through the whole of this, but basically, they've got to complete the table, then they've got to plot a graph, then they've got to calculate the gradient of the graph, including units in their answer, and then they've got to assume the volume of sodium sulfate required is proportional to the amount of iodine and deduce the order of reaction with respect to iodine. So you can see that they've got to analyse the results there. Okay, what's in the chat box? We don't have the facility to do all the practicals. Please send us the video practicals, which you can recommend. There are far too many of them. I can't send you all those videos. But I said, go into the Royal Society of Chemistry website, and you will then find the appropriate videos for yourself. There are far too many. There are literally nearly 100 videos in there. So but just simply go into your search engine and type in Royal Society of Chemistry. Do the search, and you will come up with rsc.org.uk. Click on that link, and then it is a free resource to go into the teacher's resources. Okay, and just search through and find the ones that are appropriate to you. Okay, there's an evaluation of methods. Okay, describe how to carry out recrystallization, and then this is a description. The student description of step A omitted important detail. State how method A should be changed and justify your answer. Describe what the student should do after step A and carry out step B, justify your answer, and give a reason why step D would not work, and describe how the student should obtain the crystals. So there's an evaluation of a method, and there's a method given that's got flaws in it, and the students are asked to spot those flaws and justify their answers and state the changes that need to be made. Not necessarily using the teal tube, but they do necessarily need to know how to find out melting and boiling temperatures. There's the examiner's report on that particular question I've just looked at, and this may well be worth sharing with your students. Many candidates have a good knowledge of recrystallization and have obviously carried this out as they knew the reason for the errors in the description student 1. Others would benefit from the more experience with this practical technique. Many candidates knew that the minimum amount of hot methanol should be used, but not all of them knew that this was to make a saturated solution. The use of hot filtration to remove the insoluble impurities was known by many candidates. The method described by the student to dry the crystals is frequently seen when they are describing recrystallization. I always recommend dry with filter paper and then leave it in a desiccator. That is the method that is the best and simplest to describe. Don't choose any others. Dry with filter paper and leave it in a desiccator. It was interesting to see that some candidates understood why this would not work. Okay, so that's something that perhaps is well worth sharing. And could I encourage you, please, to look as much as you can as examiners' reports, because you'll find a lot of useful information there on what students do well and don't do quite so well, and that may help influence the way in which you approach your teaching of those particular topics. There's a question on use of data. They're given some standard electropotentials. They're asked to choose the standard electropotentials to calculate E0 cell for the formation of manganate 7 acidic solution, and use the calculated E0 cell to explain why manganate 7 6 ions cannot be prepared under acidic conditions. Those of you who have read what I've written about using E0 cell to predict feasibility of reactions will know my views on that. The examiners are, Edexcel examiners are very, very keen on this particular route of calculating E0 cells. I have included in the section of the book, I have included the use of E0 cell, the reasons why I think it is a flawed method for calculating feasibility, but at least I've included how to calculate E0 cell and use it to predict feasibility. So do make sure that your students are aware of the use of calculation of E0 cell, because although it's a flawed method, it is asked for in the exam and the students need to know how to do it. Okay, I'm not going to go into any more detail. I've written about it in book 2, so please have a read of that and look at my alternative method for using electropotentials for feasibility, because I think it's useful for students to do that, because they can quickly work out the feasibility and then do this calculation of E0 cell. And then explain in terms of standard electropotentials why manganate 6 ions can be prepared in a concentrated alkaline solution. So you can see the use of data. Okay, interestingly, here's the examiner's report on this. The majority of candidates could select the correct 2 half equations needed to calculate E0 cell value and realise that the reaction does not occur because it is negative. Those candidates who calculated the positive value should have checked their working, as they were told that the reaction does not take place. I never understand why students don't do that. Don't go back and say, oh, this obviously must be wrong. So I'll go back and check it. There were some very good explanations about the effect of using concentrated alkali. However, many candidates wrote vague answers and did not make it clear which of the 3 half equations they were writing about. Some candidates showed the working for E0 cell to be negative for the formation of manganate 6 ions under standard alkaline conditions, but they then wrote a positive sign to show that the reaction would be feasible. So they just changed it around, even though their calculation was incorrect. Okay. Do we need to give Gibbs free energy and E0 cell relationship? No, Gibbs free energy is not on the international A-level specification. It is on the UK GCE specification, but not on international. But however, there is a mention in the specification that students may make use of delta G in their answers if they want to, where appropriate. And therefore, it is up to you whether or not you want to teach Gibbs free energy. You don't have to, but you can do if you want to. Okay, here are a few terms. There are lots, but here are a few terms that crop up in AO3 terminology. Anomaly. Students should be able to spot anomalies. So if they've got a series of measurements and one of them is a long, long way out from all of the others, they should recognize that as an anomaly. They should have an understanding of what is meant by accuracy and be able to differentiate that with precision. And a lot of students do not know the difference, and I will mention that in another slide in a moment. They should understand what is meant by validity and reliability and be able to differentiate between the two. And they should understand what is meant by uncertainty and error and be able to understand what is the difference between the two. And again, I've got a slide on that in just a moment. First of all, accuracy versus precision. An accurate measurement is one which is close to the true or accepted value, whereas whereas precision is if repeated measurements give the same result each time, the measurements are said to be precise. So that's the difference between accuracy and precision of measurements. Okay, the true or accepted value comes from the work of many scientists who have measured that value, agreed with it, and published the value. So in other words, it's values that are in data booklets. So you can refer to a textbook, a student book, or data tables, or indeed the internet to find these values. However, you need to be very critical of the internet sources. Some internet sources must always, the internet sources must always be checked for authenticity and bias. There are different degrees of precision. For example, ordinary mercury thermometers, that's a 0 to 110 degrees C thermometer, might only have intervals of 1 degree C, but a digital thermometer would be more precise because it can be measured to 0.1. So precision can also relate to the level of precision of a measuring instrument like a thermometer or a balance. A 4 decimal place balance has a greater level of precision than a 3 decimal place balance, than a 2 decimal place balance, than a 1 decimal place balance, etc. Okay, error versus uncertainty. Error is the difference between the measured value and the true or accepted value of the thing being measured. So a common question in AO3 is to give an example of calculation entropy change of combustion, and then the value that the candidates then get is considerably lower than the true value, and asked to explain where the error comes from. Okay, uncertainty is different. It is a quantification about the date of the measurement result. So, for example, a burette, a 50 cubic centimeter class B burette, has an uncertainty of 0.05 for each measurement made. And since you do 2 measurements in a burette, the overall uncertainty is 0.10. Do bear in mind that there are 2 measurements always made on a balance, even if you tear it back to 0. The 0.00 reading of a 2 decimal place balance has an uncertainty. So even if you tear it back to 0, you are taking 2 measurements on the balance. So you need to double the uncertainty of your balance. Using a pipette, there is only 1 measurement taken. A grade B pipette for 25 cubic centimeter grade B pipette has a measurement uncertainty of 0.06 cubic centimeters, I believe, whereas a 50 cubic centimeter pipette, I think, has an uncertainty of 0.1, I think. Okay, if memory serves me correct. Okay, so let's get on to do a little bit about marking in AO3 exams. Here's the first question that I want to look at. The use of ammonium carbonate in smelling salts is due to the formation of ammonia, which counters the effect of causing fainting. Ammonium carbonate is gently heated. It decomposes to form ammonia, water, and carbon dioxide. Write an equation. And there's the equation there. Allow multiples, or indeed, if they divide it by half, allow that. Allow H2CO3 for H2O plus CO2. Ignore state symbols, even if incorrect. Okay, so there's the first equations. I haven't put up the equations, but you should be able to work those out for yourself quite easily, I hope. You shouldn't need to remember that one. So go down through those and put a mental tick and cross next to them. Cross for the first one, of course, the formula of ammonium carbonate is incorrect. Cross for the second one, not balanced. Cross for the third one, formula of ammonium carbonate incorrect. And finally, a correct one. Good ones to show your students. Is it possible to get the recording of this training? Yes, the recording will be sent to all of you who have signed in for the session. That will happen after the session is closed. I don't know what the time frame is for you getting the recording, but you will be sent a recording of this by email. Okay, here's the other question. Complete the table. You'll see what the table is on the next slide. Okay, complete the table for a chemical test. Okay, not involving indicators and the result of each product's on this. Okay, the test is ammonia, water, carbon dioxide. Okay, so the test for ammonia is test the with hydrogen chloride. And there are lots of additional guidance over there, which you can read through in a moment, because the mark scheme will be up on the slide. The result is white smoke, and you can see that they allow white fumes and white solid, but don't award steamy or misty fumes or precipitate or cloud. The test for water is add anhydrous copper 2 sulfate, but the anhydrous is in brackets, or add cobalt 2 chloride. The result, white to blue for copper 2 sulfate, or blue to pink for cobalt 2 chloride. Okay, and for carbon dioxide, lime water or a solution of calcium hydroxide, and the result is white suspension, allow white precipitate, or allow turns cloudy or turns milky. Okay, so there's the first one. Go through that, just check through the additional guidance, have a quick read through the additional guidance before you do the marking, and then put a mental tick or cross next to each of the chemical tests and results of those tests. And then I'll share with you my suggestions as to what should be given credit and what shouldn't be. All right, placing the ammonia near to an open bottle of concentrated hydrochloric acid counts, but white fumes, hang on a second, allow white fumes is an allow notice, okay, in the additional guidance column. So white fumes is correct. Calcium chloride is in fact wrong, and because of course they haven't got a correct reagent, they can't have the white to blue mark. Lime water is correct, goes milky is correct, so this student scores 4 marks. Right, there's the second student. Have a look at that one. Well, under additional guidance, it makes it very clear for all tests, ignore anything to do with indicators. So no marks for the ammonia test. They've quoted a physical test and they're specifically asked to give a chemical test, so they can't have any marks for that. Lime water is fine, goes cloudy or milky is fine, so this student scores 2 marks. There's student 3. Well, this answer all revolves around, the ammonia one, all revolves around whether you're prepared to give the benefit of the doubt for just HCl. And I think the answer at the end of the day is that I would be prepared to give the benefit of doubt for HCl. If they'd have said add HClAQ, then they wouldn't have got it, and therefore they wouldn't have got the white precipitate mark either. But I'm prepared to give the benefit of the doubt here. Actually, white precipitate, white fumes do not award white precipitate. So they can't have white precipitate. It quite clearly says in different guidance, do not award white precipitate. That's, of course, because a precipitate is a reaction that's formed in aqueous, an insoluble solid that's formed in aqueous solution. And this is not being formed in aqueous solution. So precipitate is not accepted. And hydrous copper sulfate's okay. White to blue is fine. Lime water is fine, turns milky is fine. So this candidate scores 5 marks. Okay, complete the diagram to show how you would collect carbon dioxide obtained by heating ammonium carbonate using another test tube as the only additional product. And there's an example of the diagram over there. Allow angles to the vertical 0 to 75, so the test tube on the right-hand side can be vertical. Do not award if additional apparatus is used, i.e. a delivery tube, and do not award if the horizontal distance between the lips of the 2 test tubes is greater than 1 centimetre, and that will be something that we judge by eye on the computer screen by the examiners. Okay, so here we go. There's the first one, and of course a vertical test tube is okay, so that scores 1 mark. Next one, additional apparatus has been used, so that scores no marks. So 2 good examples to show to your students. Okay, the next question. A sample of ammonium carbonate was dissolved in distilled water and solution tested. Complete the table. So you've got the ammonium carbonate, you're adding barium chloride, was added to 5 cubic centimeters of the ammonium carbonate solution. What's the observation and what's the observed product? And hydrochloric acid was added. What's the observation and what's the observed product? And here's the mark scheme over on the right-hand side. For the barium chloride, an answer that gives white and precipitate. So they need both. Okay, so not just precipitate on its own, not just white on its own, but you can accept white solid or white crystals. Identify the precipitate as barium carbonate, accept the correct formula, and note if name and formula are given, both must be correct. Ignore ammonium chloride and ignore water if the precipitate is clearly identified. Just ignore those, okay? And for part 2 about the hydrochloric acid test, effervescence, allow bubbling, bubbles or fizzing. Ignore gas evolved because, of course, the gas is colourless, you can't see it. And the observed product is carbon dioxide. Accept the formula. Again, if name and formula given, both would have to be correct. I know it doesn't say it, but that would have applied as well. Ignore barium chloride. BaCl2 is the product. Ignore ammonium chloride and ignore water. Okay. Right, so there's your first one. Okay, observation insoluble, obviously incorrect. but the observed product is not dependent on a correct observation. So barium carbonate is okay, fission is fine, carbon dioxide is fine, so 3 marks. There's the next one. White precipitate forms is okay, barium chloride is correct, and the additional guidance says ignore ammonium chloride. So we can ignore the ammonium chloride, and that scores a mark. Precipitate dissolves is wrong. Formation of barium chloride is an ignore, so that doesn't score. Student 3. They've got the white precipitate, but they've also put down vigorous effervescence, which is incorrect, so that negates the mark. They lose the mark because they've written down effervescence. And they've written down hydrochloric acid as well as barium carbonate, and that is not an observed product, and therefore they lose the mark for barium carbonate. So this is a very good example to show to your students about how this candidate has lost 2 marks, even though they've actually given 2 correct answers. Effervescence is fine, turns lime water milky, absolutely fine. Okay. And there's student 4. White precipitate, barium carbonate, perfect. Precipitate dissolves and effervescence is fine. Okay. And carbon dioxide given off is fine. Barium chloride is an ignore. Okay, so I hope that's given you a little insight into this marking, okay? And again, you may well want to use some of these with your students. I very strongly advise you to do so. Get them to go through marking exercises. Right, teaching, doing practical work. The chemistry specification, as I've mentioned, contains a number of practical activities that form part of the subject content, the core practicals. And again, I strongly advise that the students get as much hands-on experience as practical as possible on those core practicals or demonstrations, or indeed video clips, some of which you can get from Royal Society of Chemistry. Exam questions expect the students to be familiar with these methods. So the students need to know the procedure for every single one of those core practicals, and they need to memorize them off by heart. The questions also expect the students to apply their knowledge of practical methodology to unfamiliar situations. So they need to be aware of that. The more practice you give them on that, the better. So why should the students do practical work? Well, pretty obviously, one of the answers will be so that they can answer the questions on units 3 and 6. But of course, they do gain quite a lot of valuable knowledge that will enable them to be able to answer questions on the theory papers as well. And of course, they gain quite a lot of skills that will help them in their future lives. Manual dexterity just being one, for example. And of course, if they are doing the practical work in the right way and thinking about what they're doing, and not only just following a recipe, they're gaining quite a lot of experience in analysing data, evaluating, etc. So they gain a lot of useful techniques that they can use both in their further education and also in the world of work. So more practical work you do, the better. So you've got to ask yourself the questions, are your students getting the knowledge and skills from the practical activities? And I will be coming up with some support that will help you to get your students getting the correct knowledge and skills from the practical activities, and that will be following on in just a moment. So when do you do practical activities? Before or after teaching the theory of a topic? Well, whether you do them before or after, my very strong recommendation is they should be very closely linked in terms of period of time and indeed in terms of your teaching. So teach practical work and theory work together in the same time period and draw as many links as you can between the practical work and the theory work, so the students see the two are interrelated and support one another and not totally separate. Okay, so I've talked about support material. Let's have a look at it. There are 2 types of support. There's the online support that you can get from the Pearson qualification website. There's the teach and learn materials, past papers, mark schemes, examiners reports, and teacher resource packs you can get from the Pearson website. There are also published resources. There are the student books, and if you do have copies of the Pearson published Pearson books, you will see my name on the cover of those because I co-authored them with Jason Murgatroyd. And there are lab books that you can buy as well, which may save you having to download the practicals, the details of the practicals, and printing them off. That may prove cheaper to you if you are charged by your centre for photocopying. Buying the lab books may work out cheaper. The other advantage of the lab books, of course, is that the students then have all the practicals together in one particular source, so they don't have them spread out over their folder all over the place. Okay, I mentioned teach and learn materials. There are the teach and learn materials that are available to you, and I'll show you the main website page in a moment. There's the exemplar material, the Getting Started guide, teacher math support, teacher practical guide, transition guide, past training content, scheme of work, topic guides on energy and entropy, and instrumental analysis. And I'll be going through quite a few of these one by one in the upcoming slides. There is the landing page when you click on teaching and learning materials from the Pearson website. When you go into the International GCSE qualification website, so you bring up Pearson qualifications and then click on A levels and then click on C for chemistry and then scroll down to international advanced levels, click on that, click on C for chemistry again, and it'll bring you to this page. And you can see you've got specification sample materials. Look at the course materials box. You've got specification and sample materials, exam materials. You've got teaching and learning materials. Exam materials are all the past papers and mark schemes and examiners reports. The teaching and learning materials contain quite a few of the things that I'm going to show in the slides from here on in. For example, exemplars with commentaries in the teaching and learning materials section. Here you've got marked exemplars with examiners' commentaries, so very, very similar to what I've been doing with you. They're student answers that have been marked by senior examiners, the mark awarded, and comments made about what students have done well and done not so well. So again, things that you can use with your students to give them an indication about things that students do well and do not so well, to try to encourage them into good practice. Only available, unfortunately, for AS at the moment, nothing for A2. Okay, if someone can remove that line that they've drawn, I presume they're using their iPad or something similar, it'd be very helpful, thank you. Okay, the next one is the Getting Started guide. This provides an overview of the new, well, it's not so new now because of course it was introduced in 2018, the new IEL qualification, the current one, and provides information about the content and assessment and gives you a better understanding of what these mean for you and your students. So that's well worth reading, particularly if you're totally new to Edexcel International A-level chemistry. There's the math support, which I very strongly recommend that you download and read. This covers selected topics that the students often find difficult, like mole calculations, enthalpy changes, reaction rates, equilibrium calculations, and acid-base equilibrium and pH calculations, all covered. Okay, electropotential calculations, all covered in that particular book. Please, 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 please download it and read it. It's very useful to you. Then you've got the practical guide, which is designed to support you and your students through all the elements of the practical work in this AS and A-level specification. It explains how the new requirements for practical skills can be developed through the course using both the core practicals and the other specification content. Again, please download that and read that thoroughly whenever you get the opportunity to do so. You'll find it extremely useful. It's got all the core practicals in it, and it's got lots of questions that you can ask them to supplement and improve their understanding of what the experiments are all about, and develop their knowledge and their skills rather than just the recall of how the experiment is carried out. Then you've got the transition guide. The transition guide is very useful because students, as a teacher, it's very easy to think, oh, I wonder if my students know enough from their GCSE chemistry, or have they remembered enough from their GCSE chemistry coming into A-level. Should I spend some time going through what is absolutely essential? And students often, as teachers often think, yeah, well, I really must do so. And this, of course, takes out valuable teaching time from the A-level course. The transition guide can help you overcome that by providing you with a mapping, first of all, of Edexcel International GCSE to the new Edexcel specification. It gives you some baseline assessments, which you can set them outside of class time. It gives them some summary sheets in there. It gives some student worksheets in there, gives some practice questions. And the teacher version also includes answers for assessments and worksheets. Now, there's a student version of this, which if you know that your students are going to do A-level after the summer break, you can get them to download that student guide and then go through with them some work that you would want them to do during the summer holiday, the break between GCSE and starting A-level. And that will actually help you to help them to supplement their knowledge, to support it and make sure it's there ready for starting A-level. There are lots of other things in there, so have a look at that transition guide. Some suggestions on how to teach some of the topics are in there as well. So download that and have a read through that as well. You may find that useful. The scheme of work includes recommended teaching time for the topics. Though, of course, this is adaptable according to your individual teaching needs. Got some classroom activities, it's got teaching points, it's got some suggested teaching resources. Okay. And it's got objectives for students at the end of each topic area and examples of integrated transferable skills. Transferable skills, of course, are very, very important for the students when they go on to do further education and go into the world of work. And then the two topic guides. This one has been written by George Facer, and those of you who have been involved in teaching A-level chemistry for a number of years may well recognize the name George Facer, because George has written a huge amount of resource material for the teaching of Pearson Edexcel chemistry, including student books and other resource material. In fact, I've got quite a lot of it. I'm just turned around at the moment and I can see two folders with George's name on it. A2 Chemistry Teacher Answer Guide and A2 AS Chemistry Teacher Answer Guide to lots of questions that he's set. George, unfortunately, has now passed away, but his legacy still stands because that material can still be purchased online, much of which, of course, is still relevant to present qualifications, although they were written for previous qualifications. But this topic guide was written by him specifically for this qualification, and it gives you some ideas on how to address common misconceptions in both new and previously included content, possible teaching sequences for key specification points where there's new or challenging content, and worked examples that teachers could use to support students in developing their understanding. So again, very, very worthwhile because it's written by what I would say is the best chemist that I ever worked with as an examiner. He was my chair of examiners when I first started marking A-level chemistry for Edexcel. And I gained a wealth of knowledge and understanding of chemistry that certainly influenced my teaching, my subsequent teaching of chemistry to my students. And I thank George very much for helping me develop as a teacher. The other guide has been written by David Reed, And David Reed is a lecturer at the University of Southampton. And this is about instrumental analysis. It gives you some ideas on how to address common misconceptions in both new and previously included content. One of the new contents, of course, from the previous qualification is carbon-13 NMR. It gives you some possible teaching sequences and key specification points where there is new or challenging content. And it gives worked examples that students could use to support students in developing their problem-solving skills. There are links to external websites that can be used to further students' understanding. Okay, so again, well worthwhile. I did mention there's 2 students' books, and you can see my name and Jason Murgatroyd's name on it. I and Jason co-authored the books. All the theory work in those 2 books are written by us. And the work by David Scott was the thinking bigger exercises at the end of each particular chapter. So it's the theory work is all done by myself and Jason, and David Scott did the thinking bigger work. The first book covers IAS content, and the second book covers IAL. It is not a requirement for you to purchase those books for your students. You don't have to use these resources to deliver this course. You can use any student books you like. I would, however, recommend that you get at least an inspection copy of these and read them to see how the subject content is explained, because the examiners have these books. Certainly the chair of examiners does, because I sent him 2 copies of it. And I guess the chief examiner probably does as well. And they influence the mark schemes that are produced, and therefore the way in which the topics are covered in these books will influence what is written in the mark schemes. So although you don't have to have these books for your students, I would suggest it's useful for you to have at least inspection copies, which you can often get free of charge. Although you may have to, if you work abroad, you may have to pay the postage. I'm not sure. Pearson have also published the lab book. I mentioned the lab book earlier. Okay, so you may find that purchasing the lab book is cheaper than photocopying all the details of the core practicals and handing them out to your students. That will be the case, may be the case if you're charged for photocopying per department. So that can be purchased as well. And lastly, if you've got any concerns, any worries about anything to do with this particular qualification, then contact Irene. Her email address is on that landing page that I showed you for International A-Level Chemistry, and you will have it on the slide pack that is in the resource material. Any concerns you have about this qualification, anything about the questions that have been set and the mark schemes associated with them, anything you don't understand and you want explained, contact Irene, and she will get back to you with an answer. So anything about the assessment of this, any concerns whatsoever you have, contact Irene. Very worthwhile. She is absolutely excellent. I can vouch for that because I've used her when I've had some concerns and queries, and she's got back to me with the answers very, very quickly. Or at least if it's not her, one of her subject team will do so.